Okay, number 20, the hungry bear. So look, first thing you do is you do free body diagram. So period 1, I know we already did this, but we're going to do it again. Okay, so we're doing a free body diagram for the beam. That's where it all starts. So you got to identify all the forces. So starting at the right here, we have the goodies hanging off. That's perpendicular to the beam. The goodies weigh, where does it say? 80, right here. 80 newtons. And then we have a rope, this cable. So force in a rope is called tension. We'll label that T. 60-degree angle. Okay, the weight of the beam itself. So they tell us that the beam is 200. For a perfectly uniform object that's the same from end to end, you want to put the weight of the beam in the middle because that's where the center of mass is. So boom, right there in the middle, 200 newtons. We got this bear standing on the beam. That's a force on the beam. The bear is 700 newtons. Now look, I know I already mentioned this, but I'll say it again. Normal force on the bear. Look, kids always ask about that. Isn't there a normal force on the bear? Well, yeah, there is. But are we doing a free body diagram for the bear or the beam? We're doing a free body diagram for the beam, so don't show the normal force. In fact, I'm going to erase this bear. So the bear is simply a force on the beam. Okay, now, right here, part B says when the bear is 1 meter away from the wall, find the tension in the wire and the components, right here, the components of the reaction force. This is very confusing what they mean by that. So the components of the reaction force, if you think about it, the wall is right here, right? The wall exerts a horizontal force pointing to the right. So I'm going to label that force horizontal, and it also exerts a vertical force. And if you think about it, this has to be true, right? Oops, force vertical. Look, if you look right here where the beam touches the wall has to be pushing to the right. Otherwise, the beam would break through and go to the left. The wall also has to be supporting the beam vertically, because if it weren't, what would happen? The beam would slip off the wall and fall. Does that make sense? Okay, now in reality, force horizontal and force vertical, is it two different forces? In reality, these two forces are one force at an angle. This is the force of the wall right here. It's acting at an angle. But force horizontal and force vertical are the what? The components. Okay? Now, okay, so we're ready for distances. Now look, distances have to be measured from where? When we're doing torque, where do distances get measured from? The axis. You measure the distances from the axis. For a problem like this, no point stands out as being an obvious axis. So take my advice. When you have a situation like this where there's no obvious axis, where do you place the axis? At the point where you have the most unknown forces. So here, at this point right here, we don't know force vertical, we don't know force horizontal. That's two unknown forces. Make this point the axis. Now, why do we do that? Because forces on the axis cause no torque. That means that these guys will not appear in our summing of the torques. They're going to disappear. Does that make sense? Forces on the axis cause no torque. Okay, so that's our axis. So now let's put distances in. So guys, I'm gonna make some room. We're ready to solve. I'm going to delete all of this. Okay, and let's scoot this up. Okay, so let's put distances in. We'll do this in red. All right, so we measure distances from the axis. What's the distance from the axis to this 700 Newton force, to the bear? They told us it was what? 1 meter. That's 1 meter. Okay, distance from the axis over to the center of the beam. Well, how long was the beam? 6. So how far is it to the middle? 3. Okay, from the axis over to the end of the beam. 6. So we have our distances here. Now, what's nice about the force of the bear? Well, the force of the bear, if you look at this, is the 1 meter perpendicular to the force. Yeah, when you do torque, the force and the distance have to be perpendicular. The 1 meter is perpendicular to the 700 newtons. That's going to be nice. Okay? Now, the weight of the beam, this 200, is this force perpendicular to the 3 meters? Let's check it out. Is that perpendicular? Yeah, that's going to be nice too. Okay? The 80 newtons, the goodies hanging off the end of the beam, is this going to be perpendicular to the 6 meters? Yep. That's good. Now what about the tension? Is this tension here perpendicular to the length of the beam? No. So we're going to have to do some work there. We're going to have to make, so there's 2 ways to do it. You can either make the force perpendicular to the distance, or you can make the distance perpendicular to the force. It doesn't matter which way you do it. I think here I'm going to make the force perpendicular to the distance. Okay, how many unknowns do we have in this problem? If you read the question, so part A of this problem just wanted us to do this. Free body diagram, that's this. That's what this is. Okay, part B wants us to solve for 3 things. What's the tension in the rope? What's force vertical? And what's force horizontal? If you have 3 unknowns, how many equations do you need? 3. So how are we going to get 3 equations? We're going to sum forces X, we're going to sum forces Y, and then we're going to sum the torques. All right, summing forces X. Hey, and by the way, what's the sign convention for summing forces? When you're summing forces, what will the sign convention be? Plus, minus, plus, minus. Hey man, what's the sign convention for summing torques? It's going to be clockwise, counterclockwise. Pick one as plus and the other as minus. Okay, they have different sign conventions. Okay, so summing forces. How many X forces are there? We have force horizontal and then the X component of tension. Those are the 2 X forces. Okay, so this is going to be force horizontal minus cosine 60 T. Those are the only 2 X forces. Sum of the forces always equals ma, but is it accelerating? No, so it's just 0. That's a very useful equation. All right, in the y direction, we have force vertical, right, pointing up. We also have the y component of tension pointing up. So that's going to be plus sine 60t. And then I'm just going to add these 3 together. All 3 of those point down. What do those add up to? 980. Right? This 980 is those 3 added. Okay? Sum of the forces equals ma. Is it accelerating vertically? Nope. So this goes to 0. All right, so there's the summing of the forces for X and Y. Now, torque. So let's pick a direction as being positive. Should we say clockwise positive or counterclockwise positive? Well, first let's identify what's going on here. So the axis is over here. When you're figuring out clockwise or counterclockwise, you have to have the axis, right? So what's tension doing? Is tension pulling the beam counterclockwise or clockwise? Counterclockwise. Tension is CCW, counterclockwise. And then these three forces, the 700, 200, and 80, these guys are clockwise. Okay, so let's say that counterclockwise is plus, clockwise is minus. Okay? All right, so let's start out. Let's just go straight to the hard stuff. The hard stuff is going to be what? We have to make tension. What do we have to do to tension? We got to get it what? Perpendicular to the distance, right? The distance here is 6 meters, right? That's 6 meters. How could we get that tension perpendicular to the 6, to the length of the beam? Well, just do some vector stuff. Okay, so I'm going to get the red out. So this tension here, we can either go like this. We could go boom, boom. Those are components. Or you could go boom, boom. Right? So basically we want this guy right here. This guy is perpendicular to the beam. You guys see that? This guy is, so what's this guy going to be right here? You could either say he is sine 60t, or you could say that he is cosine 30t. Either one. Right? Okay. Oops. Okay, so summing the torques up. So we're going to start with T. So the torque equation, torque equals force times distance. They got to be perpendicular. So starting with T, we're going to go sine 60 T multiplied by 6 meters. So all I did is I'm going force times distance, and I made them perpendicular. Right? All right. Now, let's go to the 80. This is easy. Minus, why is he minus? Because we said clockwise is minus. Okay, so again, force is 80 newtons. What's the distance for the 80 newtons? 6. Right? From the axis, that's 6 meters. Perpendicular. Perpendicular. Okay? Now let's go to the 200. Minus 200. What's the distance for the 200? From the axis. Boom. What's that distance? 3 meters. Minus 700. What's the distance for that? 1. And they're perpendicular. All right. In this class, what will happen to the torques? I promise you, promise, the torques will always cancel. Meaning there's going to be no angular acceleration. Okay? You're not going to have any angular acceleration in this class. Okay, so here's the sum of the torques. Now, the hard part is done. So to solve this, it becomes a system of equations. What can you do with this equation here, with the torque equation? What's the only thing we don't know in here? Tension. And by the way, this is why we put the axis here. That's the whole reason. Why did we stick the axis right here? So then FV and FH don't appear in the summing of the torques, right? So you do the algebra. I'm going to let you guys do that. And this comes out to be 342.6. Okay? That's the tension. Now that we know tension, what can we do with that? Take tension, plug it in there, right? Once you plug it in there, now you can solve for FV, right? FV comes out as 683.3. That's that force vertical. Then take tension, plug it in there. And now you can solve for FH. Force horizontal comes out as 171.3. So it's just algebra. Once you have the equation set up, the rest is algebra. Okay, the final question is how far out can the bear walk without snapping the cable if the tension, the maximum tension in this cable, in part C of the problem, they tell you that the maximum tension is 900 newtons. So the question becomes, how far out can the bear walk? Okay, so I'm going to erase that 700. The bear is the 700. So basically, you know, the bear is going to be somewhere out here, right, where that's 700. So this distance, let's just call this distance x, right? So looking at this equation here, we can solve it from this equation. So, but what we have to modify it. So what are we going to do to this torque equation? We plug in what for T? For tension, you plug in what? 900. And then this 1 meter here becomes what? X. So that's all you have to do. X is how far out the bear goes. So now you take this, you solve this for X, and you get about 5.1 meters.